Welcome to this Sharp Kinane Limited Guru session for May 2021. I'm David Kinane. This month we'll be taking a look at the BBC microbit. Like last month's Guru's focus, microbits are inexpensive little devices that students can connect to a computer to link to their coding projects. Microbits are even cheaper than Makey-Makeys and in many ways more versatile. In this introductory video we will look at the key features of the microbit, understand how they differ from Makey-Makey, and learn how to create a simple program and load it onto the microbit to run. Many classrooms are investing in robots to meet their computational thinking requirements within the curriculum. But what is a robot? By having microbits in a classroom and some well-chosen peripherals like motors, servos, wheels, gears, cardboard and a host of other cheap materials, students can design and build their own robots to meet the needs of their own inquiries. If you want to create makerspaces and open-ended computational thinking investigations in your classroom, then a microbit is hard to walk by. So let's start by looking at the main features of this feature-rich little device. On the front side of the microbit there are some clear features. The bottom rail has 5 holes in it, and on the right is the ground pin, which allows you to connect external devices to the microbit. Next to the ground is the 3-volt input and output pin to power the external devices. Then there are the remaining 3 pins, which are most often used to connect the signal control cable from the external peripheral to the microbit. You will also notice along the bottom rail that there are lots of vertical lines. These are the 17 pins that can be utilised by other external expansion boards like the Kitronic motor board, the Adafruit Cricket and many other expansion boards. In the middle of every microbit is this 25 LED array on which sensor values can be displayed, as well as messages. This array is also a light sensor and can be used to measure light intensity. To the left and right of the LED array are the A and B buttons, which can be coded separately to do different actions, and when pressed together, a third action. The microbit also has a thermometer, an accelerometer, a compass, and a send and receive antenna in it, making it a very powerful tool for students to explore the world around them. Later on we will share some ideas that we have developed and implemented in New Zealand classrooms with this little device. But first, let's look at the reverse of the microbit. The key thing to note is the centre port here is the USB port. This is how the program written on the MikeCode website is transferred via a USB cable to the microbit. Next, to the extreme right of the microbit is the 3-volt power input. Unlike a Makey-Makey, microbits can easily work whilst not connected to a computer. By adding a 3-volt battery pack, a microbit can operate and run its programs whilst not being connected to a computer. To the left of the 3-volt input is the reset button. You can use this to reset the microbit should your program run away with you. To the left of the reset button is a tiny LED. This is the LED that indicates that a program is being transferred from the computer to the microbit. It rapidly flashes as the file is transferred, and once transferred, stops flashing. That is the basic overview of the main features of the microbit. Now let's investigate how to use it. If there is one criticism of the microbit, it is the ridiculously short USB cable they are supplied with. It is important to teach students to disconnect their microbit from the project they are working on and plug in the USB cable at the computer, or purchase longer leads. Microbits come with a 3-volt battery pack supplied, and using this allows students to power the microbit away from the computer. It is worth noting that a lot of other external peripherals need more than 3 volts to be powered, so students will need to have different battery packs, 6 volts for example, to power motors. Working out the connections is all part of the computational thinking process. Now it's time to look at making our first program to run on a microbit. To do this, we need to go to the MakeCode website. There is no need to create an account or to log in. Just start to use the site and download your programs. You will notice in the top right of the screen that this site is maintained, managed and owned by Microsoft, so it's a robust and well-supported site. On the screen here you can see my recent projects, and to create a new project just click on the New Project button. Before you can proceed you have to give your project a name. You can always change it later. When your project has a name, click on the Create button and the MakeCode site will then load. Once the page is loaded, you will notice in the top left of the page that there is a digital version of your microbit. This is in fact a fully functional digital version of your physical microbit, so you can test your code in most instances before downloading to your physical microbit. In the middle column here contains all of the standard microbit code blocks. The basic blocks allow us to program the LED, the input blocks will let us program the buttons. The music blocks are interesting as there is no speaker or earphone jack on the microbit. Crocodile clips are needed here. We will be using the pins block in a moment. So to start, we want to use the input block to program button A to move a servo. Next, I want to use the servo write block in the pin section. When I add this block to the button A press input block, look at what happens to the microbit. For some, but not all blocks, the site will produce a wiring diagram and virtual setup of your hardware to test your code. We can now change the number in degrees that we wish the servo arm to move to by using this slider on the block, or just type in the desired angle from 0 to 180 degrees. Once the code is set, we can test our simple code by pressing the A button and the servo arm should move. Let's make it move back again with a button B press. Just drag out the same blocks and change the button from A to B. Look what happens when we change the pin number from 0 to 1 for the B button command. Now we get two servos and the appropriate breadboard wiring diagram, which will be easy for students to follow. To change back to a single servo, all I need to do is change pin 1 back to pin 0 and reset the angle for the servo, then test the code. Using the virtual microbit to test the code is a good scaffold for the students to use. Obviously, as they get more advanced and their projects get more complex, this feature will not support them so well. But now, it's time for us to download and test our program for real on our own microbit. To download the program, click on the download button. We then have to confirm that we want to download the file. Close these other dialog boxes, and then the .hex file is downloaded to my downloads folder, ready to transfer to my microbit. Before this though, you need to remember to have your microbit plugged into the USB cable and the USB cable to be connected to your computer. Now that my microbit file has been downloaded, I can locate it in my downloads folder. Note that even though you name your work, when they are downloaded, all files are prefixed with the word microbit. To transfer the file to the microbit, first make sure that your computer can see the microbit as an external drive. Then it is simply a case of dragging the file from the downloads folder to the microbit icon and letting go. The file is now transferred to your microbit. As the transfer happens, the indicator LED on the back of the microbit will flash rapidly and stop once the file has been successfully downloaded. Using an external 3-volt battery pack and using the same wiring setup as demonstrated by the virtual microbit, I can now test my code. This is just a simple example of how to use a microbit and to connect other peripherals to it to control other functions. There are thousands of additional cheap peripherals that can be connected to and controlled by a microbit, as well as of hundreds of expansion boards made by companies like Adafruit and Kitronic, as well as many others to further enhance the capabilities of this versatile brain of a robot. And this is the key to the microbit. It can be almost anything, enabling a myriad of projects and investigations to occur in the classroom. Some examples of projects we have designed and implemented in schools are, well, we have made remote controlled cars with a Kitronic motorboard, 2 microbits, some cardboard and 2 motors with wheels. We have made marionettes with 2 microbits and a host of servos and a cardboard box. We are currently working with a couple of schools designing and building remote controlled America's Cup yachts, again with microbits and a couple of servos. One of our students designed and built a drone with 4 engines. It didn't fly, but it worked. She proved it worked. We have created a unit using microbits as Morse code relay stations to explain how the telegraph stations of the 19th century transferred news rapidly around the world. We have created self-watering units that monitor soil moisture and water plants when they're too dry. We have had students design pet treat vending machines triggered by simple switches to distribute treats, and as an extension, random treats from random dispensers. Again, with microbits, cardboard, servos. We have conducted time gates, again with simple switches and a microbit to measure how fast objects travel between 2 points. We have even created a project on cowrie dieback to ensure that hikers clean their feet before entering or leaving the bush. All of these projects were made possible with a microbit and a few simple peripherals and lots of cardboard. In short, every classroom should have these devices as a key part of their computational thinking curriculum.